All right, cool. So I've been teasing calibration for a while now, but today we're actually going to do it. So just maybe to, again, give the overview of sort of the story I've been telling in this class and that I've been giving as the overview at the beginning of each class so far, but you know, so far so good. We started off studying super weak marginal guarantees. Okay, get the mean right on average, get quantiles right on average. And we showed you could do those things very easily. Doing them was a good idea. It would improve error of various sorts. And we showed that you could do it not just in a distributional setting, but against an adversary. And you know, you might have thought doing things against an adversary was hard, but for these marginal guarantees, like the adversarial algorithms were in some sense even easier than the batch algorithms. Okay, so we want to do more difficult things. We want to subject our predictors to more rigorous tests that can hopefully filter out things that are, for example, merely marginally consistent. And again, we want to do it both in the batch setting and in the sequential setting. Okay, so today, we sort of talked about what we were going to do at the end of last class with calibration. Today, we're going to do it. And to remind you, the premise of calibration is that our predictions should be correct, not just marginally, but also conditionally on the predictions themselves. So if I say there's a 20% chance of rain tomorrow, meaning I predict that the mean of the rain random variable tomorrow is 20%, should be that conditionally on that, meaning if I average over not all of the days, but all of the days on which I predict a 20% chance of rain, it should have rained 20% of the time. So it's no longer just a marginal guarantee, it's a conditional guarantee, and it's like a self-referential conditional guarantee. It's conditional on the prediction itself. And similarly for quantiles, if I predict that there's an 80% chance that tomorrow the number of inches of rain is less than 3, then when I look at the rain distribution, the CDF, the empirical CDF of how frequently it rained on all of the days for which I predicted this, I should find that the 80th percentile quantile of that distribution is 3. Okay, so it makes sense to talk about this stuff for means and quantiles and even other statistics. The point about calibration is we ask for our estimates to be correct, conditional on our estimates themselves. Okay, so let me remind you of some basic facts that we've gone over a couple of times, but are going to be immediately useful in our analysis of algorithms today. So first is that, at least when we were talking about mean calibration, which is what we're going to start off doing today, it's very useful to keep track of squared error, right? And we've been writing B of F, which stands for Breyer score, to denote the squared error of a classifier. It's just the expected value over a random draw from the distribution of the squared difference between the prediction we make and the actual outcome. Okay, so we sort of talked about how this is a proper scoring rule. The reason this is sort of useful when talking about means is because if I need to predict like a single number that's, that's going to minimize the squared error, the thing I would want to predict is the mean of the distribution. Okay. Now, minimizing squared error doesn't necessarily mean that I'm calibrated. So we gave last time some measures of calibration error. Okay, again, we can do this for means and quantiles, but let's start out by doing it for means. We talked about average calibration error. And in particular, last time we gave 3 definitions. Let me remind you of the sort of L2 variant, which is the one we're going to use today. In particular, we looked at the following definition of average calibration error, which I called K2, the squared error variant. And this is a measure of a model as evaluated on some distribution. And what this was so remember what calibration error is supposed to say. It's supposed to say, look, conditional on the prediction that I make, my prediction should be right on average. Okay, now there's sort of like a problem with that, especially when we start talking about measuring and obtaining calibration error from a finite sample of data, which is that I sort of can't hope to be calibrated on predictions that I make very infrequently, right? Like suppose, in fact, just to think about sort of like the limiting case, suppose I always make a prediction to like 10 trillion decimal points of precision. It's never the same prediction every day. So I only have one observation conditional on making a very particular prediction. Somehow, like inevitably, if I condition on rare events, I'm going to have lots of uncertainty about the distribution conditional on those rare events. And so it's like hard to try to promise a guarantee that conditions on arbitrarily rare events. And so the reason we're going to look at something that I'm calling average calibration error, and that, we saw it last time, but I'll remind you of the definition in just a moment. The premise is to look at the average, right? So for every prediction I could condition on, I will have some measure of error conditional on that prediction. Like among the days when I predicted a 20% chance of rain, how much did the actual frequency of rain differ from 20%? I want to allow that for predictions I make very infrequently, that error might be larger without allowing you to cheat and somehow, have large error everywhere because you make only rare predictions. And so the idea is I'm going to compute basically the expected value of this conditional calibration error in expectation over the prediction. Okay, so this is really an expectation. It's the sum over all of the predictions that I might make, all of the values in the range of my model, of the probability that I make that prediction over a random draw from the data distribution. Okay, so this is setting it up to be an expectation over the prediction I make times the squared error, the squared difference between the prediction I make. Like I said, there is a 20% chance of rain, and the actual expectation of the random variable of the label y conditional on the prediction that I make. Okay, so just to sort of stare at this for a moment, I predict there's a 20% chance of rain. Conditional on predicting there's a 20% chance of rain, there's actually some frequency with which it rains. If I was making perfect predictions, if I really, had a direct line to God and he told me the probability of rain every day before he flipped his coins, then when I predict a 20% chance of rain, that means that what he's going to do is flip a coin that has bias 20% and it rains. And so this will be 0 for every value of v, right? So first thing maybe to note, unlike squared error, which we'd like to be small, but it's just, fundamentally impossible to drive to 0, there's inherent uncertainty in what the distribution is. It's always possible in principle to have 0 calibration error, because the true conditional label probabilities have 0 calibration error. Second, this measure, since it's an expectation over the choice of prediction v, does allow that I can have a predictor that has good calibration error that nevertheless has very bad calibration error for very rare predictions. But I can't have bad calibration error for all predictions if I'm going to make this small. And so this doesn't allow me to cheat by sort of just making predictions that are always very rare to, right? Like, you know, because I am averaging over all of them. Okay. And last time we sort of defined two other measures of calibration error. This is sort of an L2 measure in that what I'm looking at is the expectation over the squared calibration error. We could also look at the expectation over the absolute calibration error. We called that K1. And we could also, instead of looking at the expectation, we could look at the max of these terms. We called that K infinity. And these are all related to one another in a way we worked out last time.
Some events that are very rare, usually we don't have them in our training set, right? So when we want to calibrate and estimate, it's not easy to consider for those very rare events.
That's true. And that's one of the nice things about this definition. So you'll be able to prove out of sample bounds for this definition, even if your predictor has sometimes makes predictions that are so rare that you've never seen them before in your training set. And the reason for that is if they're that rare, they don't matter. You know, like they will happen out of sample like only very rarely as well. And so they won't substantially affect this. But yeah, good point. Does that answer the? Okay. Yeah, that's part of the reason why we don't want to be in the business of making promises conditional on very rare events, because we just might never have seen them. But this is a way around that. Yeah.
Just wondering, what is this calibrated B? So you're saying that x1 is subject to some like distribution B? No,
that's right.
That you have a fixed B that...
That's right. So this is calibration error in expectation over a distribution. We're also going to work out later today, you know, how you might be calibrated against an adversary in the sequential setting, in which case we'll need to define an analog of this without assuming a distribution.
So this is the distribution.
That's right. So this is the definition of sort of average calibration error of a predictor over a fixed distribution. And if you had a different distribution, the calibration error of your predictor might be different. Good question. Other questions? Okay. So you know, okay. So there's like a K1 variant. You know, there's a K infinity variant. Last time we sort of related all of these using Cauchy-Schwarz inequality. This one's awfully convenient. So today I'm just going to work with this one. And just to be clear about the goals for today, what I want to do today is give and analyze two algorithms, hopefully. One for making this small when in a distributional setting, and one for guaranteeing that this is small in the adversarial setting, where the role of the distribution here is going to have to be like the empirical distribution over the transcript ex post. Okay. One other fact that we proved maybe like the first lecture, and I wrote on the board last time, but let me just remind you of it, because again, it'll be relevant to our analysis. And it's sort of the behavior of squared error as we correct a predictor to predict something closer to the mean of the distribution on which we are evaluating it. Okay, so this is the lemma that we're going to use in our analysis. Fix any distribution on labels. Call it dy, say. And let's suppose that V star is the actual true label expectation. So the expectation when I draw a fresh label from this label distribution of the label. And let's let V hat be something that's not the true label expectation. In fact, it's wrong by exactly delta. So V hat is V star plus delta. Then, if I look at in expectation over a draw of a random label, of the difference between the squared error that I get when I predict V hat, this thing that's wrong, not the true label expectation, wrong by delta, compared to what I would have gotten if I had predicted V star, the correct mean, that this difference is exactly delta squared. Okay, so we proved this already, so I won't prove it again, but just to remind you of this fact. And because this holds for every label distribution, an implication of this is that the thing that minimizes squared error overall, the predictor that minimizes squared error overall, is this function that we've sometimes called f star, that for every x maps it to the true expectation of y conditional on x. And the way you can see that is you can apply this lemma separately to for every x to the conditional distribution of y given x, right? That point by point, you minimize squared error by predicting the correct mean of the distribution, which means if I have some information x, the thing I should really do is predict the mean conditional on x. Okay, so that's why that's sort of a proof, or I'm not going to prove it again, but when we proved this fact in the first lecture, that was a proof that squared error is a proper scoring rule, which just means it is minimized by the true conditional label expectation. Okay. All right, one final definition from last time, and then we'll give and analyze our algorithm. And it's just the definition of the sort of atomic operation we are going to use to update models. And to remind you, the form of our algorithm is going to be the following. It's going to be like, let's look at our model F, and we'll ask ourselves, is it calibrated? And if the answer is yes, we shout, hooray. If the answer is no, we say, okay, well, where is it not calibrated? There must be some prediction V that it's making such that it's conditional on predicting V, it's wrong. And what we're going to do is when we find an error of that sort, we're going to fix it. We're going to say, okay, well, before you were predicting V, but conditional on predicting V, the actual label mean appears to be V prime. So whenever you predict V, you should have predicted V prime. And that's going to be the sort of atomic update that we're going to iterate in the algorithm, which we're going to call a value patch. So given a model F, and given a pair of values, V and V prime, these are just, like numbers in 0, 1. Think of V as what the model, something the model is currently predicting. Think of V prime as something that the model should have been predicting instead of V. We'll say that the following function is called the value patch applied to the model F with respect to this pair V and V prime. And I'll write it like this. It's going to be some function I'll call H. It's a function of X, but it's parameterized by some model F and V and V prime. And I'll write suggestively V arrow V prime, because what we're doing is we're taking places in which the model previously predicted V and predicting V prime. And what is this function? Well, it's nothing more than the function that predicts V prime if the function we were patching, f of x, evaluated to V and evaluates to f of x otherwise. Okay, so it's literally just saying, okay, I'll take your old model F. If it predicted V, I'm now going to predict V prime, but if it predicted anything else, I'll leave it the way it was. So think about it as taking one of these level sets, exactly one of these level sets of the old model, and shifting it. Okay. Okay. And then finally, let's write down the algorithm we're going to analyze, which I'll just call calibrate. And it takes as input a model F, a parameter alpha that specifies just how calibrated we want this model to be. And for now, we'll assume it takes as input some direct way to access the distribution D, meaning this algorithm will take it upon itself to estimate, to compute expectations over this distribution D. Now we're keeping in the back of our minds that, of course, in real life, we can't directly do that. And so eventually we're going to want to think about what happens if the distribution we give it is actually just an empirical sample from the true distribution. But for now, let's not worry about that. And let's pretend that we can take expectations over the true distribution. Okay, so what's the model do? What's the algorithm do? Well, it's going to iteratively produce some model FT. And initially F0, the first model, is just the model that it's given. T is going to keep track of what round we're currently at. Initially, T is 0. And we'd like to output some model that has calibration error less than alpha, such that this measure of squared calibration error is less than alpha. And so while the current model doesn't satisfy that property, while the squared calibration error is bigger than alpha, well, then we're not done. So what are we going to do? We're going to look for a particular value on which the prediction of the model appears to be wrong, conditionally on making that prediction. Okay, so we're going to look for the value Vt that maximizes among all of the values in the range of our current model the probability of our model predicting that value times, like the measure of squared calibration error on that value. So the difference between the value itself and the actual label expectation conditional on the model predicting that value. Okay. So this is, so this value V that we're finding, this is sort of like a big problem with the model in that, it's maximizing sort of the product of two things that could be wrong with this model. It could be wrong with this value. First, this value has large squared calibration error. Like we're predicting something that hopefully is, like substantially wrong, conditional on our prediction. But also it's not super rare because, we're taking the product of that with the frequency, right? So the hope when we select this value is we've found something that is simultaneously a reasonably frequent prediction and on which our model is substantially wrong on average. The hope being that if we can find something that sort of corresponds to a large error, a large error that our model makes frequently, then if we fix it, we can substantially decrease squared error, which is going to be the thing we rely on to argue that this process cannot go on for too long. Okay, so we've found something that is, like hopefully a big problem with the model, and now we want to fix it. So how do we fix it? Well, the first thing is we compute what is the value that the model should have predicted when it was predicting V. let's call that VT prime. And that's just the expectation of the label, the true expectation of the label, given that the model was predicting VT. Okay, if only it had, for all of these instances, predicted VT prime, then this problem we discovered wouldn't have been a problem because VT would have been equal to VT prime. And so we'll fix it. We'll patch up the model using this value patch. And so we just say, okay, well, at the next round, the model that we'll call FT plus 1 is just the model that results from applying this value patch to yesterday's model, FT, where we're shifting the old prediction VT to VT prime. And then that's it. If we ever break out of this loop, we'll return this final model FT. Okay, so that's the algorithm. The next step is to prove that it quickly returns a calibrated predictor. But before we analyze it, are there questions about what the algorithm is doing? Let's see, what do you mean by that? So certainly, okay, two things you could, that question could mean. You tell me which one you mean. One question, is there a unique calibrated predictor? The answer to that question is no. Was that your question? The other question might be also interesting. The other question is, does this algorithm, like, is this a deterministic algorithm that outputs a unique thing when you run it on some? That's right. So in some sense, like, this is a completely specified deterministic algorithm, except for tie breaking. So, you know, the argmax is a set. You know, I guess like generically there won't be any ties if you can measure things to decimal precision, but you know, you could cook up examples where there are. This algorithm doesn't really care how you break ties. And so if there were no ties, you know, like given some f, it would output some ft after some number of rounds that would sort of be uniquely specified. But if it's an example where the argmax is not unique, then, you know, like we haven't specified which path we're going to go down, and different paths would potentially lead to different predictors.
Is there a reason to take maximum time to just take support rather than alpha?
Yeah, so you're saying, like, could I just have written this algorithm as find any VT such that this quantity is large? And I guess it wouldn't be alpha. It wouldn't be guaranteed to have one of these points that was bigger than alpha. It would be bigger than alpha over m. That'll show up in the proof. We could have done that, and we could have proven the same theorem. But I guess, like, if you were actually running this algorithm, you'd want to take the maximum, because what we're going to show is that the amount of progress we make in reducing the squared error is exactly equal to this term. And so, although the way the proof is going to work is we're going to say, well, you know, if the calibration error is at least alpha, then, you know, we're going to have to find some v such that this quantity is at least alpha over m, and therefore we make at least alpha over m progress every round. And that same proof would work if we just said, take anything that has weight at least alpha over m. Like, when actually running this, you'd want to pick the biggest one because you'd want to take advantage of being able to make more progress when you can. Does that make sense?
Okay, so from my understanding, so the probability that ftx equals to v is actually determined by f, by the function f.
That's right. The determined by the function f, and of course the distribution.
Then after each iteration, you only change the fx value, but the distribution won't change. the probability that fx equals to v will
Uh,
not change.
Well, the probability that ft of x equals v doesn't, like, I've changed f, right?
Yes.
So tomorrow's probability that ft of x equals v is different than today's probability in which ft of x equals v. In particular, it's quite likely that tomorrow the probability is 0 because I just took everything that my model predicted v for and predicted something else. But yes, like calibration is this self-referential kind of thing in that the event that we're conditioning on is an event defined by the model.
So the following question is that do we allow that the range of effects to be infinite than the choice?
Yeah, that's a good question. So at the moment, so let's assume that it's finite for now, because in the theorem we're going to prove the convergence rate will depend on the cardinality of the range. And so in particular, like if the model had infinite range, it could be that for every VT in the range, this evaluates to 0. Because it could be that like it's a measured 0 event that you predict any particular thing, in which case this algorithm might never halt.
The question is, if like the FPS output is finite, can we guarantee that VT prime is within this range?
That VT prime is within this range. So VT prime might not be in the range of the original algorithm. So like suppose, so one thing that we'll note about this algorithm is that these updates do not increase the size of the range. They can only decrease the size of the range. So the updates can't increase the cardinality of the range. If yesterday there were m values that could be predicted, tomorrow there will be either m or m-1 values that can be predicted. But like if you were only predicting before, 0.3 and 0.6 and conditional on predicting 0.3, like conditional on predicting a 30% chance of rain, there was actually only a 10% chance of rain, then this is going to say every time you predict 30%, predict 10%. And so it'll change the range. It'll, before you were predicting 0.3 and 0.6, now you're predicting 0.1 and 0.6. And that's of course necessary because the thing you were predicting before might have been wrong, and we want to fix it to the right thing.
But VT prime could take any value between 0 and 1. So
Yes.
then you cannot guarantee that VT prime is within the previous range. If you set fx to like V prime, you actually increase them.
No, I don't know what you mean by increase the range. Like VT prime might not have been in the range before. Like before, maybe I was predicting, 30% chance of rain or 60% chance of rain all the time, and conditional on predicting 30% chance it actually rained 10% of the time, right? So then maybe like VT is 30%, VT prime is 10. And now whenever I was predicting 30% before, I'm now predicting 10%. So 10% was not in the range before, but the new range is 10% and 60%. So it's before the range had size 2, now the range still has size 2. The size of the range cannot increase by applying one of these updates. And that's kind of important. And, the reason it's important is because, as we're going to see, the amount of progress we make is proportional to 1 over the size of the range. And we want that, we want to talk about the range of the original model that we were fed, not the range of models that are produced while running this algorithm, which maybe we don't know much about. Okay. And in general, and it's not coming up yet, but when we, in a couple of lectures, get to multi-calibration, the questions you're asking are going to become more relevant, because when we get to multi-calibration, we will be talking about updates that can potentially increase the size of the range. In general, to avoid problems like that, we're going to want to snap this quantity that I'm treating as sort of an arbitrary real number right now to some kind of discrete grid. Like you'll figure out some error tolerance, you're happy predicting probabilities of rain up to 1% error. If the prediction was 10.03%, I'll snap that back to 10% exactly so that we can control the size of the range. Those are good questions. Okay, other questions before we, yeah. I'm not sure I follow. That is exactly what this algorithm will do if the cardinality is initially 1, right? Like if the cardinality is 1, right, meaning the function is constant, then we say, okay, it predicts a 50% chance of rain every day. We say, okay, well, actually, like overall, the chance of rain is 30%, not 50%. And so this, what the update will do is it'll say, okay, before you were always predicting 50% chance of rain, now predict a 30% chance of rain, and then we'll be done. You'll be perfectly calibrated, and the cardinality will be 1. Yeah. Which is maybe getting at something else, right? Like this is a post-processing algorithm. We're taking as input a model, and we're correcting it to be calibrated. Now, there's many ways to be calibrated that correspond to, interesting models or uninteresting models. One way to be calibrated is to just have a constant function that predicts, that sort of ignores everything and just predicts, the population-wide mean. If that's what you input into this thing, if you input any constant function, what you will get out is a constant function, just the constant function that predicts the right mean. On the other hand, you could do something much more sophisticated than that, right? If you plug in a much more sophisticated algorithm, you'll get an even more sophisticated one out. Because what we're going to prove is that not only does this result in a calibrated predictor, but in a calibrated predictor that has better error. So this will improve your model. If you plugged in a dumb model, you'll likely get, you'll get a slightly better dumb model out, but it won't be guaranteed to be doing anything clever. You were just predicting a constant before, you'll still just be predicting a constant, it'll just be the right constant now. On the other hand, if you were doing something clever that actually had low squared error, or it just wasn't calibrated, this algorithm won't ruin that. You'll get something back that is calibrated and also has better squared error than you started with. Yeah.
Can you use the description cardinality as almost a proxy for the accuracy of your original model? Like if your original model say has cardinality, 10, or the range, but it's essentially just like making random predictions. So likely that's just going to devolve into like a mean at the end.
Yeah, something like that. Like right, that's right. So like in some sense, right, like if your model's clever, it's probably making very fine-grained decisions, has large cardinality. And this will basically, well, yeah, I don't have a formal statement here, but like your example is exactly right. Like if your original model was sort of needlessly using large cardinality, like it was making random predictions, this will very likely collapse it down to a constant predictor. Because if your model was making random predictions, say, we live somewhere where on average it rains 30% of the time, and your model was just, making predictions based on, I don't know, like something entirely unrelated, like the outfit of whoever hosted the Oscars, Perfect. Sunspots, yeah. So suppose it was making predictions based on sunspots. Assuming sunspots, in fact, have no correlation to rain, then conditional on the prediction of the algorithm, which is conditional on sunspot activity, the propensity to rain will still be just the baseline propensity. It'll be 30%. And so what this will do is it'll look at every level set. It'll say, look, you're predicting something, but what you should have predicted on this level set is 30%. And it'll shift everything to 30%, and you'll get a constant predictor back. Yeah, like basically if the predictions you were making were entirely uncorrelated with the label, they'll all get collapsed into constant predictions. And the fact that I can give you back a constant predictor that has better squared error than your complicated thing will be good evidence that your original predictor was not very good. Good question. Other questions, good or bad? I feel like if I say good question, then I scare away people who have bad questions. So I also welcome bad questions. Okay. Okay. So let me first give a foolish analysis of this, because the foolish analysis will be the template for the analysis we actually need to do for more sophisticated guarantees down the road, like multi-calibration. But then we'll see that there's a better, simpler analysis for this if all we're interested in is regular calibration. Okay, so this is like the silly theorem. But the silly theorem is the one you should pay attention to because that's the one that's going to be relevant to the rest of the course. It happens that there's, this has some special structure that lets you get a better theorem. Okay, so after T rounds, sorry, first thing we might want to, what do we want to prove about this? Maybe the first thing we want to prove about this is just that it will act that it's actually an algorithm. It'll halt and output something. Because a priori, it's not obvious. There's this while loop that says, while the model is not good in the way that I want, keep going. And until we've proven that this is guaranteed to make progress in some sense, you might worry that forget about talking about the properties of the model it outputs. You might worry that we never get out of the while loop, that you just never output anything. Right. So what's obvious from the definition of the algorithm is that if we output something, then it's calibrated, because that's the condition that causes us to output something, right? We break out of the loop exactly when we have calibration error less than alpha. So the thing you might worry about is that we never break out of the loop. So what are the things we want to prove about this? We want to prove that it halts after a reasonable number of steps. If we prove that, then in particular, we've proven that it's output something that's well calibrated, because that's exactly the halting condition. And then we also want to prove that we've decreased the squared error of our original model, because if the only thing we wanted was to output a calibrated model, right, there would be a much less compelling algorithm that did that. It takes as input a model F, it doesn't even look at it, it throws it in the garbage, and then it outputs a constant predictor that just predicts the mean label outcome. And that would be a calibrated predictor, but you would have preferred your original predictor. So we want to prove that the thing halts. If it halts, it must output a calibrated prediction. And then we want to prove that it outputs something that actually has better squared error than what you started with. Okay. So the claim is that after T rounds, where T is bounded by M over alpha, remember that M is the cardinality of the range of the model that we plug in. So our convergence bound does depend on the cardinality of the range of the model. After T rounds, this algorithm, calibrate, halts, and outputs some model ft such that two things are true. One, the calibration error of the model at most alpha, and two, if I look at the difference between the squared error of the model I started with and the squared error of the model I ended up with, that this is exactly equal to the difference between the calibration error of the model I started with minus the calibration error of the model I ended up with. Okay, and in particular, the premise is that, you know, your model was poorly calibrated before, so the calibration error has decreased. We've decreased it down to alpha at least. And so in particular, the squared error has also decreased, right? And so there's no trade-off here. In fact, this relationship is exact. The decrease in squared error is exactly equal to the decrease in calibration error. So somehow, if your old model had calibration error, it was very directly leaving performance on the table. Like, there's a very simple way to decrease the squared error by exactly the amount of the calibration error of the old model. Okay, that's what I want to prove. And just foreshadowing, like, the reason this is like the silly theorem is this is way too many rounds. Like, in fact, for this algorithm, even if I ask for perfect calibration error, like alpha 0, although this theorem suggests it should take infinite time, in fact, it'll be done after like m rounds. Theorem clear? Okay. Let's prove it. Okay, so the first thing I want to note, although unfortunately I just erased the definition of calibration error, but remember what the definition of calibration error is. It was just the sum over all v of this term here, right? So, right, like calibration error was just the sum over all v of this thing we're maximizing over here. And the premise, like if we're not done yet, right? Well, calibration error is at least alpha. The sum over m terms that looks like this is at least alpha. They're all non-negative. If I sum over m things, m non-negative things, and get alpha, at least one of those things that I'm summing over had to have value at least alpha over m. Otherwise, I didn't have enough stuff to get up to alpha. Okay. So at any round t, before halting, well, by the halting condition of the algorithm, I know that the calibration error is at least alpha, and therefore I know that if I look at this quantity that for now I'll call delta t, which is just the quantity I'm maximizing over for the value Vt that actually realizes the maximum. So let's say delta t is the probability that my model predicts Vt, and Vt is the thing that realizes the argmax, times the difference between, you know, the squared difference between the prediction of the model, Vt, and what it should have been predicting, the expected label mean given its prediction. That this thing has to be at least alpha over m. Right, so the Vt that is the argmax here has to evaluate when you plug it into this expression to at least alpha over m, because the calibration error, which is at least alpha, is the sum over m terms that look like that. Okay. So maybe first some obvious stuff. So like, therefore, if I look at the calibration error, the updated model, well, what can I say about that? What was the calibration error of the updated model in terms of the calibration error of today's model? Right, what's calibration error? It's just the sum overall of the elements of the range of this term. What I've done is I've selected one element of the range, the one that maximizes that term, and I've shifted the prediction from V to V prime, which is exactly the expectation of Y. So I've zeroed out that term. And I haven't changed things elsewhere. So what can I say about the change in calibration error? Yeah, it's gone down by, like exactly delta T. And in particular, that's at least alpha over M. Right, so the calibration error of tomorrow's model is exactly equal to the calibration error of today's model, delta, right? Because, like the calibration error is just the sum over all values V of this term. And what this patch operation has done is it has zeroed out this term because we've made VT exactly equal to the expected value of Y, given that the prediction is VT. And it hasn't changed the calibration error in any of the other buckets because these predictions form a partition of the range. Okay, so the change in calibration error is exactly delta. And delta is at least alpha over M. And so, this is at most, or this is at, at most yesterday's calibration error minus alpha over M. Okay. So immediately we get convergence, right? Because the labels are between 0 and 1. The predictions, let's say, initially are between 0 and 1. And so, like each of these terms, well, it was the product of a probability that's between 0 and 1, and the square difference between two numbers between 0 and 1. Each of these terms is between 0 and 1. In particular, even since the probability that the model predicts something is exactly 1, even when we sum up over all of these terms, we get a number that's between 0 and 1. And so we know, in particular, that like the calibration error of the initial model was at most 1, right? Like calibration error is a number between 0 and 1. The calibration error of any intermediate model, well, it's at least 0. It can't go negative. And if every step is decreasing the calibration error by alpha over M, that means that the number of such steps cannot be larger than M over alpha because, like what's the best case for maximizing the number of steps? It was if the original model was as miscalibrated as possible, that would be calibration error 1. Each of the steps decreased the calibration error by as little as possible, by only alpha over M. Even in that case, and in the end, we got all the way to 0. Even in that case, you couldn't have more than M over alpha updates because each of them is decreasing this number that started at most 1 by at least alpha over M each time. Okay, that's why the algorithm has to halt after at most M over alpha updates. Make sense? Okay. So the thing outputs something that is calibrated. Okay, but remember that's not so impressive. I could have just output like the label mean and a constant function that would have halted after 1 round and output something that was calibrated. So maybe the more interesting thing is to show that the decrease in squared error is exactly the decrease in calibration error. Question?
Can also get you're zeroing out one term at each step, right? And there are scale steps.
Yeah.
Seasons and n.
That's right. So that's why this is a silly theorem. So you're right. So for this particular algorithm, because we're only asking for this like marginal calibration guarantee, indeed, you can argue that it halts after m steps. That's right. That's right. Exactly. So that is why I wrote the word silly here. But this is a template for the arguments we're going to use for multi-calibration that doesn't have this property. Formally, in multi-calibration, we're going to be talking about different ways of dividing up the space that are not disjoint. And when they're not disjoint, this argument that it halts after m steps doesn't work anymore. Okay.
Maybe bad question.
Perfect. Well, first bad question of the course.
If it's really going over n different things and zeroing them out every time, right? Then like, do we need to use something that like updates in this way, or can we simply go through all of the different sets and like zero them out one by one, not updating until like updating them all at the same time?
Can you do them all in parallel? So you have to be a little bit careful because these updates can collide, right? So like, you know, suppose I'm predicting a 0% chance of rain, 10% chance of rain, 20%, 30%, 40%. And I say, okay, like I'm miscalibrated in the 10% bucket. When I predict 10%, it's actually raining 30% of the time. So now I've changed sort of, I've changed what is the 30% bucket. So anyways, I think long story short, yes, you can do that, but you have to be a little careful in arguing it. I'm not gonna, the reason I'm giving like the silly theorem is because this form of argument, while it is correct for simple calibration, is no longer going to be useful for us when we move beyond simple calibration. But I think you are right that in this case, what you could do is you could say, okay, F defines a partition of the space. We're going to just come up with a new predictor that predicts the mean of each of the partitions defined by F, and that new predictor would be calibrated.
This is gonna be a nicer structure for the later thing.
Yeah. The other thing that maybe might be a little bit tricky to prove in that setting, but like you can, there's a version of this you can prove, but like you can argue that this iterative algorithm actually halts after only m steps, and that it still satisfies this property that the squared error is decreased by exactly the calibration error. And so in particular, you can get down to 0 calibration error, and the squared error is decreased by exactly the original calibration error. If you did it all in parallel, it would probably still be true, but it might be, you'd have to think a little bit about how to like argue this, just because maybe it wouldn't be hard. I think you're right that you could do it all in parallel in this case, and it wouldn't be hard. Good question.
You can call them back at least so that we can, you know, keep that question.
Yeah, well, I'm still waiting on a bad question. That was unfortunately a good question.
Okay, I'll try again.
Okay. But challenge for the rest of you. Okay, but we want to prove the second part of the theorem, that the decrease in squared error is exactly the decrease in calibration error. Okay, so some notation. Let's say that when I write dvt, this means I'm talking about my original data distribution conditioning on the event that ft of x equals vt. And similarly, when I write d of not vt, what I mean is the original data distribution, conditioning on the event that the prediction of my model is not equal to VT. Okay, so it's just partition space, like the data space into two parts, where my model predicts VT and where my model doesn't predict VT. And I can look at the conditional distribution on both of those. Okay. So what is the squared error, the difference between the squared error of my model after the update on the distribution and the squared error of my model before the update on the distribution? Well, I can divide this into, squared error is just an expectation, right? It's like the expectation over the distribution, it's like an average over the distribution of f of x minus y squared. So I can divide up this average, this expectation, into two parts. Like first I'll take the average over the part of the distribution on which my model predicts VT. Then I'll take the average over the part of the distribution on which my model doesn't predict VT. So let's do that. I have to weight them appropriately. So this is just the probability that my model predicts VT times the difference in squared error between my new model on now the conditional distribution, conditional on my model predicting VT, and the squared error of my old model now on the conditional distribution, conditional on my model predicting VT. Plus, okay, so I just computed the squared error on one part of the distribution. I need to compute it on the other part as well. So plus the probability that my model doesn't predict VT times the difference in squared error on that part of the distribution. The squared error of model ft plus 1, null distribution, conditional on not predicting VT, minus the squared error of ft on the conditional distribution, conditioning on not predicting VT. Okay. So the second term, what is it? What's the difference in squared error of my two models, ft plus 1 and ft, on the part of the distribution on which ft does not predict VT? Zero, because the two models are the same on that part of the distribution, right? Like the update only changed the model conditional on predicting VT. So the second term, this is 0. So it's only the first term that matters. Okay. So this is equal to just the first term. So the probability that my model predicts VT, okay, times the squared error. Okay, but now, and this is where it would be good to remember my decrease in squared error lemma that I had on the board, but at the beginning of class, but has now been erased. But let's just remind ourselves of what it said, right? Like, what did that lemma say? It said if you have a distribution, okay, and what you're predicting on that distribution is just a constant. Okay, so you have an arbitrary label distribution and you're predicting just a constant. What you really would have liked to predict to minimize the squared error is the constant that was equal to the conditional label distribution. And in particular, if you were predicting something that was wrong by delta, then by predicting the correct thing, you will decrease the squared error on that distribution by delta squared. Okay. Now, let's think about this term here. We're looking at the distribution that is conditioning on our model predicting VT. So this is some, like on this distribution, we are predicting a constant. We are predicting VT on this distribution. Okay, so we're not doing anything complicated. By definition of the conditioning event, we're predicting a constant. And what are we, okay? And that's what our old model's doing. What's our new model doing? It's also predicting a constant. It's predicting a different constant. Instead of predicting VT, it's VT prime. Now, what is VT prime? VT prime is actually the thing you should be predicting. It's the actual conditional label distribution on this distribution. Okay, so delta is just the difference between VT and VT prime. And so the decrease in our squared error will be delta squared, which is just VT minus VT prime squared. That's what our lemma says applied to this scenario. Okay, so this term, this decrease in squared error on this conditional distribution, our lemma says is exactly VT minus VT prime squared. Okay, so let me pause. There's only a couple more steps. This is the main one that requires like thought and remembering the property of the important property of squared error. So are there any questions about how we got from here to here? Okay. Now this is exactly the quantity we call delta t. Right? This is the product of the probability we predict VT times the difference between VT and, well, this is just the thing we were calling VT prime squared. Okay, so this is exactly equal to what we call delta t. And remember, delta t is exactly the difference in calibration error between ft plus 1 and ft. So this is exactly the difference in calibration error between ft plus 1 and ft. That's what we noticed over here. Okay. And so we said, okay, at every step of this algorithm, when we transition from ft to ft plus 1, we decrease the squared error by exactly the amount that we decrease the calibration error. And so if we just apply this observation for every step, what we get is that the difference in calibration error between the difference in squared error, say, between our initial model and our final model is exactly equal to the difference in calibration error between our initial model. Okay, does that make sense? This is why it was convenient for us here to work with squared calibration error, because of this exact relationship here.
Worked with, say, non-squared knowledge error, would there be an exact relationship with absolute value?
There would not. You could still prove this, you know, like, I guess the squared calibration error is, let's see, which way did the relationship go by Cauchy-Schwarz? It was like, I guess, squared calibration error only smaller than absolute calibration error, because squaring numbers that are less than 1 only makes them bigger. So wait. Yes, smaller. Normally squaring things makes them bigger. So if they're less than 1, they get even smaller. Good. And by Cauchy-Schwarz, this is like less than square root of squared calibration error. So like this thing results in, so the exact relationship does not exist for absolute calibration error. But like if you, yeah, exactly, you can go through this relationship. So like if you made the squared calibration error less than alpha squared, then you would have also made the absolute calibration error less than alpha.
K2 of f is less than b of f.
Yes.
So it's like
They're not just shifted. Or if you want, they're shifted. That's right. So one thing that is true that I'm not sure if we'll get into in this class, we'll see, but there's actually a decomposition of squared error into two sort of orthogonal terms. You can write squared error as the sum of calibration error and something called sort of like refinement error. So basically like why does your model have high squared error? There's two reasons. Well, like it might be miscalibrated. If it's miscalibrated, we've just proven that like there's no reason to have high squared error because you're miscalibrated. Here's an algorithm. Here's a very simple post-processing that just eliminates that source of squared error. But you can also be calibrated and have high squared error because you're not making very refined predictions. Like I could be just predicting a constant everywhere. And so there is a decomposition of squared error into two terms, calibration error plus the rest. The rest is called refinement error. And you can always eliminate the calibration error part of it. The refinement error part might be irreducible, right? Like it might be that the distribution is such that you can't make good predictions, and so you can't drive the refinement error to zero. But there is you can write squared error as calibration error plus something else. And this is sort of a proof of that. Yeah.
The previous discussion, if we're done in parallel or we don't split, will they lead to the same result?
Yeah, good question. Okay, so let me try to talk through why actually, even if you plug in alpha equals 0, this will halt after m rounds. And then maybe in talking through this, we can figure out if you might as well just have done it in parallel. Okay. So like, why did we call this a silly theorem? Like, if we said alpha was, 1% or something, 0.01, this would say it halts after like 100 m rounds, but like, actually it halts much faster than that. If alpha was 0, this would say it might never halt. In fact, it should still halt, after like m rounds. And so, okay, so let's think about why. And maybe it's helpful to divide these updates into like two different sorts. Let's call one of them a collapsing update and the other one a sustaining update. So let's say that a sustaining update is one for which when I shift v to v prime, the model wasn't already predicting v prime anywhere else. So I'm just taking one of the level sets and I'm relabeling it, and I'm not collapsing it into another level set. A collapsing level set, a collapsing update would be one in which I take v, and wherever I was predicting v, I start predicting v prime, but like I was already predicting v prime for other stuff. So now I've collapsed two levels. So first, let's imagine that I don't have any collapsing updates. They're all like sustaining updates. Okay, well then, when I do one of these updates, I zero out the calibration error on that level set, and it never increases again because that level set never changes because there's never a sort of collapsing update that smashes something into it. Okay, so I'm really just going over each of these level sets and zeroing out the error. And after I get to all of them, I have 0 calibration error, and I might as well have done that in parallel. Like my previous actions had no effect on like the order didn't matter because by the time I got to level set, V10, it was the same as when I initially started.
There are two groups. One would predict 16%, another 30%, but the truth is just the other way around. So a prediction by 60%, the truth is 30%, and prediction 30% is 60%. So if we do this in sequential, we pick up them. For example, take the 30 and fix if you fix it. It's 6%. Now, the prediction, the range only contains one value is 60. But actually, we need to fix it again. So the average will have a 45%. So,
Yeah.
if we done parallel, we will get the perfect result. Like we just sequentially.
Okay, good. So I claim that even right. So you're giving an example where there are these collapsing updates where, when I update 30 to 60, I've squashed these two level sets together. And okay, and so I want to. Okay, so first I claim that even if there are collapsing updates, the sequential algorithm should still halt after at most m rounds. And I think the reason for that is because, like what we're gonna allow is that, fix the partition on elements induced by the initial predictor, F0. Okay, so that predicts 10%, 20%, 30%, 40%. That's gonna like change as we start updating the model, but let's just think about the initial partition. And what we're gonna say is that like we should update each of those partition elements at most once, or sort of, right. And so each of those partition elements might get like an initial update, at which point we've zeroed out the calibration error for that partition element. And now the question is, okay, well, what happens if a subsequent update merges with us? Will it now have like ruined the calibration error on this bucket and cause me to need to do it again? And I think the answer to that is no, because I've zeroed out the calibration error here, meaning, now I'm predicting VT prime, and that's the true conditional label distribution, the true conditional label mean. If a subsequent update causes some other bucket to predict VT prime, that's because on the partition it just relabeled, the true conditional mean was also VT prime there. And so I still have zero calibration error here. Okay, now what your example points out is that when we have these collapsing updates, doing it in parallel and doing it sequentially do not lead to the same result. Both of them will lead to zero calibration error. Both of them will decrease squared error, but in your example, doing it in parallel leads to the better model with lower squared error. I don't know if that's always the case, though. It's an interesting question.
It's more likely to increase the size of the range if we down sequentially. Because every step we can merge some additionally like we down the parallel it's still possible, but it's less likely to merge.
Yeah, so I haven't thought about this. It would be interesting if you could, here are two worlds, neither of which I can immediately think of how to rule out. Maybe you can. So you've just given an example where when you do it in parallel, you result in lower squared error than when you do it sequentially. I could imagine a world where there's another example where things are reversed, where you do it sequentially. When you do it sequentially, you get lower squared error when you do it in parallel. Or I could imagine a world where that can never happen and you can prove a theorem saying doing it in parallel always results in lower squared error than doing it sequentially. I'd be curious which of those is the real world.
If we done parallel, we visit one region with fixed area, and we may revisit the region and introduce back some error, new error. And that leads to the worst problem.
So did you answer the question? But like, okay. Well, if you think of the answer, that strikes me as an interesting question. I don't know what the answer is to it. If you think of the answer, tell me, and I will be interested. But cool. And I guess that goes back to Natalie's question. There are differences between doing it in parallel and doing it sequentially, although both work to get some version of this theorem. Although again, it's not. Let's see. Is it out? So when you do it sequentially, you get exactly this theorem, except you say it halts after at most m rounds instead of m over alpha. But in particular, the decrease in squared error is exactly equal to the decrease in calibration error. When you do it, it's probably still true if you do it in parallel, I guess. You could Well,
Well,
no, that can't be because,
well, how not be done after M round? 'Cause you're only doing it-
well, it's definitely done after M rounds. But we just had an example where whether you do it sequentially or whether you do it in parallel, you get different models that have 0 calibration error.
State what the example is.
Yeah, so the example was either, there's 2 kinds of days. It rains 30% of the time or 60% of the time. And the model I started with gets it exactly backwards. Like when I predict 30%, it's really 60% and vice versa. And so if I do it sequentially, I look at 30%, the 30% days, I say, oh no, you're wrong. It rains 60% of the time on these days. And so I predict 60%. And now I only have 1 bucket. And so now I update the 1 bucket, but I end up with a perfectly calibrated constant predictor. If I do it sequentially, sorry, if I do it in parallel, then I swap the buckets and I have 2 buckets. Also perfectly calibrated, but now more refined. And so the second model will have lower squared error. But the first one, so the change in squared error in both of these things is different. But the change in calibration error is the same. So in the sequential case, the change in squared error is exactly equal to the change in calibration error. In this particular example, in the parallel case, the change in squared error is even bigger than the change in calibration error, which is consistent with the possibility that doing it in parallel is like always better. But I don't know if there's another example where it's reversed, but it does mean that you can't prove exactly this theorem for the parallel case. You can't say the change in squared error is exactly equal to the change in calibration error.
Sorry, what's the P squares? You're running over the constant, but shouldn't, once you go to the 60% bucket, the things that,
When I go to the 60% bucket, everything's in the 60% bucket.
or everything's in the 60% bucket, but some of those things are miscalibrated still, and those things get swapped into the 30% bucket.
Well, but now at round 2, my predictor is the constant predictor that on every example predicts 60%.
Yes, I agree with that. Okay, but the final
But-
final is.
No. The final predictor is also a constant predictor, because now what do I do at round 2? I say, well, okay, there's only one thing in the range, 60%. Whenever I was predicting 60%, I should have been predicting whatever is halfway between 30 and 60%, and I shift the whole thing down. Right, so like these updates, the point is they can collapse level sets, but they can never produce, an update can never increase the range. So, okay, so this is interesting, right? So doing it in parallel does not have the property that the decrease in squared error is equal to the decrease in calibration error. This example proves that.
What if you could show basically that, like, if you collapse things, that can only make things work because of your squared error, right? Like if you end up with more buckets at the end.
Maybe, but it's also not obvious to me whether doing things in parallel necessarily results in fewer collapses. You could get collapses doing it in parallel too. So maybe, anyways, okay, homework problem. So everyone prove that doing it in parallel is always better than doing it sequentially, in that the change in squared error is always at least the change in calibration error, or give a counterexample saying that's not the case. Post it on the Slack, since this is the first homework assignment, and I don't know if any more are coming. This will constitute 100% of your grade in this class. Okay, good. I was worried about evaluation in this class. Let's see. Let me tell you how to. All right, let me tell you something about how to do this for quantiles. It's quite similar, so I won't go into full detail, but let me define what is quantile calibration error, how this algorithm would change, and how the analysis changes. Okay. So by analogy to mean calibration error, we can also define quantile calibration error, right? So remember, like when I'm purporting to predict like an 80th percentile quantile, our notion of like marginal consistency was that 80% of the time, the label should be less than my prediction. Okay, and so the calibrated version of that asks that that should be true, even conditional on my prediction, right? 80% of the time, when I predict the 80th percentile quantile is 50, the truth should be less than 50. Similarly, 80% of the time when I predict the 80th percentile quantile is 20, the truth should be less than 20. Okay, so just the same thing as the marginal guarantee, except I want it to hold conditional on my prediction. Okay, and so let's say that average squared calibration error is the following. I'll call it Q2 squared, I guess, quantile calibration error. I'll call it Q2 for quantile instead of K2. And again, it's just, you know, we face all of the same challenges as before. We don't want to have to be very accurate if we occasionally predict something, you know, like we want to allow that if we have some occasional predictions that we can have large error when conditioning on those occasional predictions without allowing us to cheat by only making very rare predictions. So we'll define this notion of calibration error again in expectation over the value of our prediction. Okay, so our quantile calibration error is again in expectation over the value of our prediction. So summing up over all of the values in the range of our model of the probability that we predict that thing of now our sort of marginal quantile consistency error on that conditional distribution, conditional on predicting that thing. So just the target quantile we're trying to hit, like 80%, minus the actual frequency with which the label is less than our prediction, conditional on the fact that we predicted that the 80th percentile quantile was V squared. Okay, so this is squared quantile calibration error. It's just sort of the natural analog of mean calibration error, where what we had here before for means was just our marginal mean consistency error on the conditional distribution, conditional on our prediction. And I've just swapped that out for our marginal quantile consistency error, again, conditional on our prediction. And once again, you can define, you know, this is sort of the squared version, but you could define the absolute error version. You could define the L infinity error version, and you have exactly the same relationship between these as you had before. In particular, you know, the squared quantile calibration error is at most the absolute quantile calibration error is at most the square root of the squared quantile calibration error. And the L infinity quantile calibration error is at most the absolute quantile calibration error is at most m times the L infinity quantile calibration error. And these have the same definitions and proofs as for mean calibration error. Okay. And just as squared error drove the analysis of this algorithm, remember pinball loss is going to be the potential function that that sort of drives the analysis of the very similar algorithm that's going to give us quantile calibration error. And just to remember the connection, like what was driving this analysis, it was like this lemma that said that if we went from predicting something that was delta far from the mean of a distribution to predicting something that was equal to the mean of the distribution, that we reduced the squared error by delta squared, and that gave us sort of exactly one term in the sum that corresponded to the mean calibration error. We had a similar lemma that allowed us to relate improvements in marginal quantile consistency to improvements in pinball loss. Okay. So so these algorithms are very, very similar. So let me not try to introduce it entirely from scratch, and I will do the annoying thing of that'll make it hard for you to take notes, but there are notes elsewhere of just writing the changes. Okay. So the algorithm will have a different name. Let's call it Quantile calibrate instead of calibrate, but it'll take as input similar things. Now, of course, you could be calibrated with respect to different quantiles, right? There's the 10th percentile, the 20th percentile, the 30th percentile, and so on. So an input to the algorithm will be the target quantile Q that you want to be calibrated with respect to. And, we're not going to halt when we satisfy, when we have a predictor that has low mean calibration error. We'll halt when we have a predictor that has low quantile calibration error. And we're not looking for a value that has high, such that conditional on that value, we have high mean consistency error. We're going to look for a value such that conditioning on that value, we have high marginal quantile consistency error. So the thing we're going to try to maximize, okay, it's still going to be the product of the frequency with which we predict that value and something else, but the something else is now going to be the difference between the target quantile that we're trying to calibrate with respect to and the probability that the label is less than our prediction, conditional on our prediction. And everything else is the same, right? Like, what are we going to do? Well, if we've got high quantile calibration error, we'll find a place where our quantile calibration error is especially bad, where both a level set that is both like frequent, like the probability of hitting this level set is large, and on which we do poorly, the marginal quantile consistency error conditional on that level set is large. Oh, and then, right, we won't update to the mean of the distribution, we'll update to the target quantile of the distribution. So VT prime will be the value V that minimizes the difference between Q and the probability that Y is less than V, conditional on lying in this level set. And if this is a continuous distribution, then the minimum will be at 0, and so VT prime will be exactly a qth quantile of the conditional distribution, conditional on our prediction. Okay, so we found a place VT where conditional on predicting VT, we were not getting the right quantile. We compute a VT prime, which is the right quantile for the conditional distribution, conditional on yesterday's predictor predicting VT. And then we just fix our predictor. When previously it predicted VT, which we just established was not the correct quantile conditional on the prediction, we replace it with the correct quantile conditional on the prediction. Okay, so the sort of most natural adaptation of the mean calibration algorithm to quantiles, we just halt when quantile calibration error is small instead of mean calibration. We look for a level set that corresponds to high quantile calibration error. We fix it by predicting the right quantile. Everything else is the same. Okay. And so what's the analogous theorem? Given any model F, with range M, and any target quantile Q, why don't we just give the non-silly version of the theorem? Quantile, so we can set alpha equals 0. We might as well ask for perfect quantile calibration error. Quantile calibrate halts after at most M rounds, because once we, each round zeroes out the calibration error in one of the level sets, and whether we do it sequentially or in parallel, they never sort of get unzeroed out. So it halts after at most M rounds. That argument is exactly the same for calibration and mean calibration error, for quantile and mean calibration error, because in both cases, the calibration error is just the sum over a bunch of terms that look like this, one for each level set. And what the update is doing is zeroing out this term for the level set it is operating on. Okay, so it halts after at most T iterations. And outputs a model FT. Okay, such that the calibration error of FT is 0. Okay, and let's remember now the difference, one sort of important qualitative difference between our quantile progress lemma with respect to pinball loss and how that related to our mean progress lemma with respect to squared error. Remember, for squared error, we didn't care what the distribution looked like. If we were predicting something other than the mean, if it was delta off from the mean, and then we shifted our prediction to the mean, we improved our squared error by delta squared. for quantiles and pinball loss, there was like this annoying caveat because right, the thing is like I can have two numbers that are very, very close together on the real number line, but that are very, very far apart in terms of quantile space. Right, like, you know, I could have numbers t and t plus epsilon and some distribution so that t is like the 0th percentile of the distribution and t plus epsilon is the 100th percentile of the distribution. Like all of the action in the distribution, it's just like compressed into this little area that has width at most epsilon. And like pinball loss is, you know, some reasonable like one Lipschitz function, right? So if I like shift my predictor from t to t plus epsilon, I can't expect that the pinball loss is going to change by more than epsilon, even if I really made a huge jump in quantile space. And so, and yet that's kind of the kind of thing we want to say. We want to say that if we make big corrections in quantile space, we will make sort of quantifiable progress on pinball loss. And so in order to say that, we needed there to be some relationship between, you know, values on the real line and their corresponding quantiles. And the way we did that is we assumed that the underlying distribution was Lipschitz, which just meant that if I wiggle, you know, if I wiggle my number around by like just a little bit, I can't change the quantile value by, you know, that much. Okay. In particular, we had this assumption that the distribution was rho Lipschitz, which just meant that if I wiggle, you know, if I move from predicting t to t plus epsilon, right? So I changed my predictor by some epsilon. I shouldn't have changed the quantile of that predictor by more than rho times epsilon. Okay, and that was sort of necessary. Okay, so that's going to come in for sort of the corresponding part of the lemma that says not only will this output something that's calibrated, quantile calibrated, but it'll output something that is only better as measured in terms of pinball loss. How much better it's going to be, but like it will only be better, but how much better it's going to be will depend on the Lipschitz constant of the distribution. Okay, so, and if the underlying distribution is rho Lipschitz, then if we look at the pinball loss of the final model, okay, that is less than the pinball loss of the model we started with. How much less? Well, now all we can say is if we ran for t rounds, then in each of those rounds, we decrease the pinball loss by at least alpha over m rho, where rho is the Lipschitz constant. So for sure, the pinball loss will be less, right? So this algorithm, just as our algorithm for mean calibration, will result in a strictly better model, this time as measured by pinball loss. But whereas for squared error and mean calibration, we were able to say the change in squared error was exactly equal to the change in calibration error. Now we can't say that anymore. We can only bound, you know, come up with an upper bound on how much the pinball loss has decreased. And that upper bound will depend on the Lipschitz condition on the distribution. And that's sort of, you know, like unavoidable. Again, if all of the distribution is in, if all of the action in the distribution is in some incredibly narrow interval, we can't expect that like wiggling around the numbers in this tiny interval are going to substantially change the value for any Lipschitz loss function. Okay. Yes, let's take a break. What is the time? 3:30. Okay, yeah, why don't we take, I don't know, 15-minute break? Does that sound good? All right, let's finish up quantile calibration. I think I've been convinced in the meantime that the parallel version of the calibration algorithm always results in lower squared error than the sequential version. So maybe the homework assignment is now not to figure out if that's true or not, but to prove it.
I don't disagree with that, but I sort of have like a question. Is that, I think that's definitely true in the way that we frame this, where we are saying that we can update it with like access to the tradition. If we're doing it updates based on a sample, I feel like then you actually have a, like, then there actually may be a trade-off where collapsing earlier and recomputing might be beneficial.
That's, yeah, but I guess,
About it as like where we're updating this model, but we have access to the true distribution under like sort of arbitrary levels of partition.
that's right. Interesting. Okay, so if there's never any collapsing, the two things are equivalent. If we have exact access to the distribution,
Conditional on some arbitrary starting rule. So like the quality of the model under the parallel scheme is like purely dictated by the number of partitions that we give it. If we give it more starting partitions, it's going to perfectly.
that's right, I guess.
Gonna update everything.
That's right. I guess the collapsing, the sequential version will result in a partition that is like the original partition will be a refinement of the final partition that results from the sequential model. And given that you, in every element of the partition, are predicting the mean of that partition, the mean of the labels on that partition, you're always, you should always, I think, have lower squared error if your partition is like a refinement, which is maybe the sketch of the proof for why the parallel version is better than the sequential version. Okay, now we haven't talked about sample complexity yet. I guess it would be relatively straightforward to think about sample complexity in the parallel version, because now we're just estimating a mean on different subsets of the data. And, you know, we should have tight bounds on how well we can estimate that mean as a function of the size of each of the partition elements. We certainly can't promise that the sequential algorithm will do better than that, because the sequential algorithm could, as far as we know, not collapse anything, in which case we have exactly the same estimation problem. I guess so then the question is, if it does collapse things, might it be that?
Yeah, I mean, it was, again, like I was originally thinking about it for of the updates like happening in reality, where they would have been based on an estimate of the truth, not,
Yeah.
like having this sort of like property of getting it right.
Mm-hmm. Yeah, it's an interesting question. If there's ever, my gut instinct is that the parallel version should also have better sample complexity, but maybe that's part B on the homework. Yeah, like, would you ever actually want to run the sequential version for any reason? Okay. So let's finish up, I guess, quantiles, and then, you know, the next thing on the agenda is sequential prediction, but I guess we don't really have time to do all of that today. So maybe I'll just finish up quantiles and we'll do sequential prediction next class. Okay. So the first part of the theorem, that the thing halts after m updates, even M updates in parallel is sort of exactly the same as what we've already talked about for means. Every round we're zeroing out sort of exactly one of the buckets on which our quantile calibration error is just a sum over the, and there's only M such buckets. So the algorithm can only run for M rounds. The thing that's a little bit different is the change in pinball loss. It's similar, but we need to use pinball loss instead of squared error, and we need to invoke sort of a different progress lemma. The progress lemma we prove for pinball loss instead of squared loss. Okay. So ultimately, like what we want to do is, our theorem in the end is about the change in pinball loss of the final model compared to the initial model. But what we will bound is round by round, what is the change in pinball loss, going from round t to round t+1, and we'll just sum those all up at the end. So we're interested in what is the pinball loss of the model that we have at round t compared to the pinball loss of the model that we have at round t+1. And just as it was for means, we can, right, like what do squared error and pinball loss have in common? Well, they're the expectation of some function over the distribution, right? So it's the average of something over the distribution. For squared error, it was just, y minus f of x squared. For pinball loss, it's this sort of like tilted absolute value function. And so in particular, it's like separable across the distribution. And so we can sort of do the same trick we did last time. We can say, well, the pinball loss, it's just the expected value of this function over the whole distribution. We can divide that up into appropriately weighted versions of the expected value of this function on the distribution conditional on predicting some value v, and the expected value of this function on the distribution conditional on not predicting some value v. Okay, so like the commonality here, that like the fact we're using in partitioning things this way, that's common between squared loss and pinball loss, is they're both just the expectation of some function over the distribution, and expectations are linear. Okay, right, so we can divide this up into two terms. The first is the probability that our model predicts v times the difference between our pinball loss, which remember is just the expected value of this function that we called LQ, evaluated at our model, and the label. It's for yesterday's model, the difference between this and the same quantity evaluated at today's model. And this is the expectation conditional on our model predicting v. Okay, and then there's another term, right, which is the probability that our model doesn't predict v times the difference in pinball loss conditional on our model not predicting v. But just as when we argued this for squared loss, that second term evaluates to exactly 0, because by definition, our two models, ft and ft+1, are exactly the same, conditional on not predicting v, conditional on ft not predicting v. ft and ft+1 differ exactly on those elements for which ft predicted v. So when we condition on ft not predicting v, the two models are the same, and so the expectation of any function of them is the same on that distribution. Okay, so in fact, the difference in pinball loss is exactly this. It's just the probability that the model predicts V times the difference in pinball loss conditional on predicting V, because the other part of the pinball loss, the part on the distribution conditional on FT, not predicting V, the two models are the same. Okay. Now this is where we need to apply our sort of pinball loss progress lemma. This is at least the probability that our model predicts V times delta squared over rho, where delta is the difference between Q, our target quantile, and the probability that Y is less than V, conditional on our model predicting V. Okay, so this is hearkening back to, I don't know, the second lecture when we proved this progress lemma for pinball loss, and we proved that if you've corrected a problem with marginal quantile consistency that was on the order of delta, right? You got the quantile wrong by delta, and your distribution was rho Lipschitz, then you've decreased your pinball loss by at least delta squared over rho. Okay, this was the moral equivalent to our sort of progress lemma with squared error, except now it really necessarily depends on the Lipschitz parameter of the distribution. Okay. So since we performed an update at round T, right? Since the algorithm did not halt round T, well, it must be that the quantile calibration error for model FT was at least alpha, because that was the halting condition. And what was quantile? Oh, so in particular, we know that it's got to be that the probability that our model predicts VT times the sort of the squared quantile calibration error conditional on our model predicting VT. That this, which is just in our new notation, the probability that our model predicts VT times delta squared, this has to be at least alpha over m, because quantile calibration error is the sum of m non-negative terms, each of which looks like this. And so if I sum up m of them and I get alpha, at least one of them, in particular the largest one, had to be at least alpha over m. And that's how we picked VT. We picked the largest one. Okay, and so rearranging, this just says delta squared is at least alpha over m times the probability that ft of x equals v. And so in particular, the progress we made at this step, which was delta squared over rho times the probability that ft of x equals v, I guess, the probability of ft of x equals v cancels out. And we get that this is at least alpha over m rho. And since this is the decrease in pinball loss at every iteration of the algorithm, if we ran it for capital T iterations, then our pinball loss must have decreased by at least capital T times alpha over m rho. Okay, makes sense. Okay. Cool. Okay, so now we know how to easily take a model that is not calibrated, and at least in the batch setting when there's a distribution, and at least when we have access to that distribution, when we can confidently estimate expectations without worrying too much about how, we know how to fix calibration error, and we know how to do so, right, both for means and quantiles in a way that improves our models. Okay, so there's no reason to be either for means or quantiles. There's no reason to sort of settle for miscalibrated models. There's no equivalent of like a, mean variance kind of trade-off. Like calibration error is sort of just bad. You can remove it not just for free, but like removing it improves your model. What I want to do next time is I want to think about how to do what we've done today in the absence of a distribution, right? So in this adversarial model. And this is maybe we've seen something already in the adversarial model. We've seen how to do marginal mean prediction. And maybe the examples of these dumb algorithms for like marginal mean and quantile prediction in the adversarial model made you think less of the adversarial model. It was sort of very easy for means. We could just predict that whatever is going to happen today is just what happened yesterday. For quantiles, we gave a slightly more clever algorithm, but we noted you could have just ignored all of the data, the features and the labels, and just a q fraction of the time predicted 1, and a 1 minus q fraction of the time predicted 0. It is substantially less obvious how to, against an adversary, come up with calibrated predictions. And maybe sometime when Ricky's in the class, he can sort of tell you about the history of this. So Ricky Vora, who sometimes attends, and Dean Foster, who had been also at Penn until recently, they were the ones who first proved that you could be calibrated against an adversary. And my understanding is they had a very hard time getting the paper published because nobody believed the result. It seemed implausible. And then I think initially the proof was complicated, but there's now a relatively simple proof. Anyways, this is all to say, it's not at all obvious how to do this, how to come up with predictions that are calibrated against an adversary. But we're going to be able to do it. And so, when we do it next class, I want you all to ooh and ah, because it's cool. Like, it's not obvious how to do it. Maybe, without looking at the notes, maybe like think about it over the next week. What would you do to try to be calibrated against an adversary? And then next week we'll show how to do it. So I'll see you guys next time.